Dear student, I am Dr. Harold Thomas, Professor in Applied Geology, Dr. Hari Singh Gaur Vishwavidyalaya Sagar. Today, I will deliver my lecture on paired metamorphic belts. Hope it will be useful for you. Try to be regular in course. The rock of any metamorphic area were usually undergone polyphase deformation and polymetamorphism. To work out the metamorphic history of any steady area on the basis presence of the mineral, their assemblages and related fabrics in the different rock types. The appearance of index minerals like sterlite, kyanite and sillimanite in the metaphylites, the presence of hornblende, anthophyllite, sphene and plagioclase in the amphibolites are utilized for interpretation with the help of the concept of Barrovian zone. Metamorphic phases and grade, the range of metamorphism in the area is established. Barrow in 1912 first recognized his zone of progressive metamorphism in Darledian of Scotland. It was thought that this sequence chlorite, biotite, garnet, sterlite, kyanite, sillimanite was typical of all orogenic belts. During that time, Miyashiro, working in Japan in the 1950s, found that the sequence of progressive mineral development were not like the classic Barrovian type. He observed evidence for a high pressure type and a low pressure type metamorphism. To explain this, he introduced the idea of metamorphic phases series or barric types. Miyashiro in 1961 simply stated the metamorphic phases series is the sequence of metamorphic phases that are observed in a transect across a metamorphic belt. The Barrovian sequence chlorite, biotite, garnet, sterlite, kyanite, sillimanite, that is green schist, epidote amphibolite, gaulite is one such phases series. Miyashiro originally recognized three different phases series. First, a geolite, prehenite, pumpelite, blue schist, eclogite type. Second, a typical Barrovian type characterized green schist, epidote amphibolite, gaulite type characterized by paragenesis of kyanite, sillimanite type. And third, an abukama type of green schist, amphibolite, gaulite characterized by the paragenesis of andalusite sillimanite type. The abukama type is named after the Abukama region in the Japan and is similar to the Buchan type of the Darledian because he recognized that these different phases series presented different pressure temperature trends as shown in figure 1. Miyashiro called them barric types. First, high pressure temperature or glaucophene jadeite blue schist eclogite type. Second, intermediate pressure temperature or kyanite sillimanite type. And third, low pressure temperature or andalusite sillimanite. Sometimes geographical region are used with this barric types. For example, Senbagwa, a high pressure temperature region in Japan for glaucophene jadeite Barrovian for kyanite sillimanite, and Buchan or Abukama, a low pressure temperature region in Japan for andalusite sillimanite type. Now switch to plate tectonics and metamorphic phases series, the discovery of plate tectonics in the year 1960s provide a new framework within which to view metamorphism. Mearsiro in 1961 had correctly recognized that the observed metamorphic phases series is a function of the tectonic environment. Moreover, he recognized that different phases series are encountered in different orogenic belt and in different tectonic settings within orogenic belts even before the evidence of plate tectonics provided a framework for their interpretation. After the discovery of plate tectonics, it became clear that glaucophyne jadeite type metamorphism is associated with subduction zone metamorphism. W.G. Ernest, who recognized that the study of high pressure temperature metamorphism could provide valuable information about the dynamics of subduction zone and the evolution of plate tectonics over the time. See figure on the screen 1, 2 and 3 diagrams created by Ernest in 1976 to show the relationship between metamorphic phases and plate boundaries. In figure 2, you can see on the screen a divergent plate is shown. Isotherms shown in figure 2a and b are blown up at the ridge because this is the focus of upwelling mantle and intrusion of mid-oceanic basalt. In figure 2b, the metamorphic phases are superimposed on the cross section of the ridge. With increasing depth of the ridge, one observed a low pressure phases series with geolite phases metamorphism giving way to greenschist and eventually amphibolite and gaolite low pressure varieties. Near the magma chamber, because new crust is originally created continuously at ridge crest, the metamorphic phases shown in figure on the screen figure 2b will migrate laterally with time. Hence, it is possible that entire oceanic crust is metamorphosed to the amphibolite to gaolite phases at the base. In order to convert unmetamorphosed oceanic crust, basalt and gabbro into metamorphic greenschist and amphibolite, water must be added to the rock. In the absence of added water, no metamorphism will take place. Therefore, it is not necessary that the entire crust is metamorphosed simply because the temperature are metamorphic temperatures and the metamorphism may be restricted to plate where the water has access. It is interesting to note that many metamorphic rocks have been found from oceanic ridges and fracture zones and have been recovered in drill cores. Metamorphic rocks have only been found where channel for the penetration of water are available. Metamorphism in the oceanic crust may therefore be restricted to the vicinity of fracture zones. See figure 3 on the screen is shown a convergent plate margin. The isotherms in figure 3 are blown downward into the subduction zone because the subduction zone process carries cool oceanic lithosphere downward into the mantle in the vicinity of the Iceland arc. The isotherms are blown up because hot rising magma carry heat from the mantle upward. In the Iceland arc, the metamorphism is a low pressure temperature type, that is Andalusite sillimanite type. See figure 3b on the screen. The sequence of phases encountered going down subduction zone is zeolite, prehnite, pumpelite, blue schist, eclogite. In contrast, the sequence of phases encountered going down in the Iceland arc is zeolite, prehnite, pumpelite, green schist, amphibolite and gaolite. See figure 3b on the screen reveals that there is a polarity to the metamorphic phases in the subduction zone. This is the increase in metamorphic grade from zeolite, prehnite, pumpelite, blue schist, eclogite take place along the deep of the subduction zone, because this is where the isotherms are blown down. Ernest in 1971 recognized that this polarity is the key to determine the depth of the ancient subduction zone. He reasoned that unless the subduction complex became completely inverted, then the depth of the ancient subduction zone should be in the direction of increasing metamorphic grade. In Japan, the metamorphic grade increases from zeolite phases through blue schist phases, with some green schist and amphibolite overprinting as one traverses to the northwest. The metamorphic progression terminates abruptly at the median tectonic line, which is a major structural boundary. To the northwest of this line, the metamorphism is low pressure Andalusite sillimanite type. This juxtaposition of high pressure and temperature and low pressure and temperature metamorphic phases type has been called by Mayashiro a paired metamorphic belt. The low pressure temperature metamorphic belt is the ancient Iceland arc, which in the case has been thrust up against the subduction complex. Metamorphic zones in the Franciscan complex of California here clear progression from zeolite phases through prehnite, pumpelite phases to blue schist phases. As one progresses, eclogite are restricted to isolate blocks within low grade rocks. The other examples are California, Alps, etc. Dear student, today in this lecture I have discussed about the paired metamorphic belt. In this topic I have covered the following heads: introduction, metamorphic zones, plate tectonics and metamorphic phases series, and subduction zone polarity and pair metamorphic belt. For further studies, please read the textbooks, references and links given in the text.